Let us see about current source inverter, different types of current source inverter, and in that we will see about the load commutated current source inverter. What is an inverter? It converts a DC quantity into an AC quantity at desired magnitude and frequency. There are two types of inverter based on the source input. First one is the voltage source inverter, which we have studied in the previous videos. So in voltage source inverter, we know the input voltage is constant and the output voltage is independent of the load. So this is the input voltage we give for a voltage source inverter, and always we get a square wave output irrespective of the nature of the load. In current source inverter, the input current is constant and the output current is independent of the load. So if you have a voltage source as input, input voltage is constant and output voltage will be independent of load. In current source inverter, input current is constant and output current is independent of the load. So this is a current source which is given as the input for the inverter, and your output current waveform will be a square waveform. So how to get a current source? So we know this is the symbol of the current source. How to get a current source? You take a voltage source, connect a high inductance in series with the voltage source. This will act as a current source. So because inductance is a property to limit the rate of change of current. So this inductance helps to achieve a constant current from the source. So thereby you can get a current source from the voltage source. So what is a current source inverter? So a current source inverter converts DC input current into AC current. And the input current is constant but it is adjustable. What do you mean by that? If you take this diagram, this is a current source inverter. The input is coming through a chopper. So what is a chopper? It is basically a DC-DC converter whose output is controllable. So here you are getting a controllable DC input. So this DC voltage is connected in series with a large inductance, so that this combination acts as a current source for this inverter. And the output is a AC one. This output AC current is the nature of the waveform will be independent of the load. Let us see the features of current source inverter. So power devices used in current source inverter should be able to withstand large reverse voltage. That is, it should be able to block the reverse voltage also. So normally thyristors and GTOs can be used. This is a thyristor. And when we use a thyristor in DC circuits, we know that we have to use some type of commutation to turn off the thyristor. So normally a simple capacitor can be used to commutate the thyristors. There are different types of current source inverter. One is load commutated current source inverter, which we will see in this video. And the next one is forced commutated current source inverter. So as the name suggests, load commutated CSI means due to the nature of the load, the thyristors get commutated in a current source inverter. We call that as a load commutated current source inverter. In forced commutated current source inverter, we have to use some external capacitors to turn off the thyristor. This is a circuit for load commutated current source inverter. So the input to the inverter is a constant current source I, and it consists of 4 thyristors T1, T2, T3 and T4, and the load is connected between the two legs. It is a resistive load and a capacitor is connected in parallel to the load. The charging and the discharging of this capacitor helps to commutate the thyristors. So the initial charge on the capacitor is assumed to be minus V1, that is this side is negative and this side it is positive. So it is considered to be minus V1. And this is the voltage across the resistive load V0, where this A point is considered to be positive with respect to B. Now take the current. So this is the total current, that is the AC current, and this is the current through the capacitor and this is the current through the resistor. So IAC is equal to, that is here T1 and T2 will be conducting in one mode and T3 and T4 will be conducting in the other period. So when T1 and T2 are conducting, the current through this one will be equal to I. So IAC is equal to I, and the output voltage V0 is equal to the capacitor voltage, that is equal to the initial charge on the capacitor. So that is equal to minus V1. And what is I0? This is a resistive load. So V and I are in phase. So I0 is equal to V0 by R. So that we can write it as minus I1. So there are basically two modes of operation. In mode 1, T1 and T2 are given gate pulse. So that is the period 0 to T by 2. That is the total time period we have taken as T, and half of that is T by 2 time period. So for first half T1 and T2 will be conducting. It means that we are giving gate pulse at 0 for this particular two thyristors. At T by 2 we will be giving gate pulse for the T3 and T4 thyristor. So that period is T by 2 to T. So let us see about mode 1. So in mode 1 we have seen that T1 and T2 are given gate pulse, and the initial charge on the capacitor we have taken as minus V1. So V0 is equal to minus V1, I0 is equal to minus I1. Okay, so this is the current path. So now you can find here that this IAC, that is equal to I, because when T1 and T2 conducts, current flows, the total current flows through this line. So IAC is equal to I. And IAC I can write it as IC plus I0. That is KCL. Apply KCL at node A. You will get IAC is equal to IC plus I0. Now we will find what is IC. So IC is, from this equation you find what is IC and substitute IAC and I0 values, you will get this one. And you have to find what is the V in. So V in is this voltage, input voltage. So this end, when T1 conducts, is connected to point A, and this point, lower point, is connected to B. So V in is equal to this voltage. So what is this voltage? Minus V1. In mode 1, we can see that T1 and T2 are in conduction and the current flows from A to B, and the capacitor polarity changes from minus V1 to plus V1. So V0 will become plus V1, that is, this you will get around T by 2 time period. When T is equal to T by 2, this is the state. Now I0 we can find, that is V0 by R, and IC, this capacitor current is IAC minus I0, but I0 is plus I1 here, so you substitute it. So V in is equal to V1. So V in is equal to, because it will be connected to A point, so V in is equal to plus V1. This is the equivalent circuit when T1 and T2 are conducting. So you have two parameters, this is resistor and a capacitor. So let us write the loop equation for that. So I naught into R plus this voltage, you have to consider the initial charge on the capacitor, that is V1 also. So this is a differential equation. You can find the solution for this differential equation and considering the initial condition, that is at t equal to 0, we have I naught is equal to minus I1. So with that, if you solve this equation, you will get this as the solution for the current I naught. Next we will see mode 2 at t equal to t by 2, where the mode 2 starts. T3 and T4 are given gate pulse, that is T3 and T4 are given gate pulse. So initially T1 and T2 were conducting, now you are giving gate pulse for T3 and T4. So this current changes, so the current starts to flow in this direction. And you see the charge on the capacitor, and so this IAC now changes the direction, so it becomes minus I, and other equations are similar. So IC you can write IC is equal to IAC minus I naught. With that you can substitute I naught value, you will get IC. And Vin is, now you see T3 and T4 are conducting. So Vin is now connected to point B. So this end is connected to point B. So we consider the voltage to be minus V1. So this is the equivalent circuit during mode 2. T3 and T4 are conducting. So now we will write the KCL equation. So IC is equal to, already we have calculated what is I1. So it is minus I1. We will find what is IC and Vin. So Vin is equal to plus V1 because Vin is now connected to point B and you have plus here. So Vin is equal to positive. Now we can do one thing. Let us tabulate all the values we have calculated for the previous modes of operation. That is, take the time period t equal to 0 to total time period t, and this t less than t by 2 is just less than the just before t by 2, and this is just after t by 2. So while drawing the waveforms, you will understand what it is. So for mode 1, T1 and T2 is on for 0 to half cycle, that is T by 2, and mode 2 starts from T by 2 to T, and we have tabulated all the parameters. Now you see the waveform. So 0 to T by 2, T1 and T2 are conduction, and other half T3 and T4 are in conduction. Now you see the V0 and I0 waveform. You see here V0 and I0 will be similar because it is a resistive load. Only magnitude will change. So this is minus V1, this is minus I1. Plus, plus, minus. So same thing will be for I0. So V0 and I0 are drawn on the same scale. So here initially you have minus V1, V1, V1 and minus V1. So here you have minus V1 and here plus V1, again minus V1. So it is not a problem. Next case, when you see the collector current, you can see one thing. Here you have I plus I1 and here I minus I1. So here it is I plus I1, then here it is I minus I1. But after T by 2, that is after T3 and T4 are turned on, you will get this as the capacitor current. So it becomes minus of I plus I1. Again at T, you will get minus of I minus I1. So you can see one thing, this parameter is just reverse of this one. Okay, and this one is reverse of this one. So you can remember like this. So this magnitude and this are minus of that one, and similarly this and this are minus. Okay. Then if you see Vn, V input, so it is minus V1 initially, then it goes to plus V1. After T3 and T4 are on, it will go to minus V1 again. So this is before T by 2 and this is just after T by 2. Okay. So you can draw the waveforms. Now we have already seen that the AC current is the sum of these two currents. So if you see the IAC current, you add these two, you will get I as the magnitude. So add these two, I. Add these two, you will get I only. So whenever you add these two, you will get I only. So I or minus I. Okay. So this is the output current. So there are some design considerations for this current source inverter. So this equation we have already derived in mode 1. Next, V0 is equal to I0 into R. So you can use the same equation. Then we will calculate what is the circuit turn-off time Tc. So how to calculate this? Equate this equation to 0. You will find what is Tc. And this circuit turn-off time should be always greater than SCR turn-off time for reliable commutation. And if you use it for a low frequency application, you will get a square wave output for V0 and I0. And if you have a high frequency application, you will get a sine wave output. But there is always a limit on the frequency, operating frequency. So if you want, if you decrease the T or increase the frequency above a limit, the circuit turn-off time will decrease, which will lead to commutation failure. So let us see the disadvantages of current source inverter. Always a minimum load is required at the output. So there is a limitation for the operating frequency, and at light loads and high frequency, the inverter will give you a sluggish performance. So let us see the difference between voltage source inverter and current source inverter. Let us see the difference between voltage source inverter and current source inverter. In voltage source inverter, we have DC voltage as input. Here you have a current source as input. So here input voltage is maintained constant and there input current is maintained constant. Here output voltage is independent of the load. You always get a square wave irrespective of the load. Here in current source inverter, output current is independent of the load. And here the load current waveform and magnitude depends on the nature of load impedance. Similarly, in a current source inverter, the magnitude of the output voltage and its waveform depends upon the load impedance. In voltage source inverter, we normally connect a feedback diode so that it works under non-resistive load. But in current source inverter, we don't need any feedback diodes. Here the commutation circuit in voltage source inverter is complicated, whereas it is easy in case of CSI as we require only capacitors. And in voltage source inverter, we can use power BJT, power MOSFET, IGBT because they can be operated at very high frequencies. So normally it is preferred. But in current source inverter, the devices has to withstand large reverse voltage. So normally thyristors or GTOs are used. So the points to remember here are current source inverter converts DC to AC current. It is fed with the adjustable current from a DC source of high impedance, and the amplitude of the output current is independent of the load. Thyristors and GTOs with reverse blocking capabilities is used. And there are two types of CSI, load commutated and force commutated. For force commutation, you can use capacitors. If you like the video, do subscribe to Read Electric Vehicle channel. Thank you.